A power system stabilizer PSS is a control device used in power systems to enhance the stability of the grid by damping out oscillations in the system. These oscillations, known as power swings, can occur due to disturbances such as sudden changes in load, generation, or faults within the network. The PSS works by adjusting the excitation system of a generator, thereby controlling its output to help maintain system stability. How PSS works: signal input. The PSS monitors various signals within the power system, such as generator speed, frequency, and electrical output power. These signals provide information about the system's dynamic behavior. Excitation systems with high gain and fast response times greatly aid transient stability synchronizing torque, but can also reduce small signal stability damping torque. Power system stabilizer PSS control provides a positive contribution by damping generator rotor angle swings, which are in a broad range of frequencies in the power system. These range from low-frequency intertie modes typically 0.1 to 1 Hz, to local modes typically 1 to 2 Hz, to intra-plant modes about 2 to 3 Hz. The low-frequency modes, commonly called intertie or inter-area modes, are caused by coherent groups of generators swinging against other groups in the interconnected system. These modes are present in all interconnected systems, and the damping is a function of tie line strength and unit loading factors. Weak ties due to line outages and heavy system loads can lead to poorly damped intertie modes. PSS control can generally provide significant improvements in intertie mode damping by applying stabilizers to most units that participate in power swing modes. PSS performance is often evaluated from the damping of the local mode, the generator swinging against the rest of the power system. This mode is usually at frequencies between 1 and 3 Hz. Stronger system ties and lighter loading tend to give higher local mode frequencies, and weaker ties and heavier loading tend to give lower local mode frequencies. PSS performance must be designed to provide acceptable performance over a wide range of system conditions, which may result from different operating conditions such as lines out of service and varying load levels. Signal processing. The PSS processes these signals to detect any oscillations or instability. It uses algorithms to determine the appropriate corrective action needed to dampen these oscillations. Control action. Based on the processed signals, the PSS adjusts the excitation voltage of the generator. By modifying the excitation, the PSS can influence the generator's reactive power output, which in turn affects the system's voltage and frequency stability. Power system stabilizers, or PSS, are designed to correct the phase error present in fast excitation systems. PSS typically monitor the system frequency or MW output at the generator terminals. Based on the changes the PSS detects in system frequency or MW, a voltage signal is input to the automatic voltage regulator. The automatic voltage regulator compares the PSS voltage signal, the monitored voltage, and the set point voltage to calculate an error signal to send to the exciter. The PSS portion of the voltage regulator's input helps ensure that any adjustment the excitation system makes to generator voltage based on the voltage regulator's error signal is done in a manner that helps reduce system oscillations. The PSS will ensure that the excitation system voltage output has the correct phase relationship with the oscillation it is trying to eliminate. The power system can naturally damp most higher frequency above 1.0 Hz oscillations. The power system may require assistance with damping some low-frequency oscillations. PSS are tuned to correct an excitation system's response to low-frequency oscillations. A PSS is typically set to detect oscillations in the inter-area or intra-area modes approximately 0.05 to 1.0 Hz. If these frequency modes are present, the PSS will send corrective voltage signals to the automatic voltage regulator. If the oscillations are outside of the PSS's tuned range, the PSS will not send any corrective signals. Without a PSS, fast excitation systems may cause system oscillations to sustain themselves or to grow in magnitude. With PSS installed, fast excitation systems can perform their job of increasing steady-state and transient stability limits and also help eliminate oscillations. This may prevent oscillatory instability. All units with fast excitation systems should be equipped with well-tuned PSS in these regions. It is important that a large number of units have operational PSS. A 1000 megawatts generator with a properly tuned PSS may only contribute 1 to 2 MW of damping. This small amount of damping from an individual unit is not enough damping to make much of a difference. PSS are typically installed in the majority of larger units in the problem area. The combined effect of many PSS has a significant impact in damping oscillations. PSS can also be used for local oscillatory stability concerns. These PSS are typically designed and tuned to deliver a substantial amount of damping. PSS may also be tuned to provide positive damping at frequencies different than the inter- or intra-area modes. Damping oscillations. The primary function of the PSS is to introduce a damping torque to counteract the oscillations. This damping helps to reduce the amplitude of oscillations and brings the system back to a stable state more quickly. Benefits of PSS: enhanced stability. The PSS improves the overall stability of the power system by reducing the likelihood of sustained oscillations, which can lead to power outages or system failures. Increased power transfer capability. By stabilizing the system, the PSS allows for higher levels of power transfer across transmission lines without compromising the reliability of the grid. The PSS contributes to the reliable operation of the power system, ensuring that generators remain synchronized and that voltage levels are maintained within acceptable limits. Implementing a PSS is a cost-effective way to enhance system stability compared to other methods, such as building additional transmission lines or upgrading infrastructure. Applications of PSS in large power plants. PSS is commonly used in large thermal and hydroelectric power plants where maintaining grid stability is crucial. In interconnected power systems, PSS is particularly important in interconnected power systems where oscillations can propagate across the network, affecting multiple regions. In renewable energy integration, with the increasing penetration of renewable energy sources, PSS helps manage the variability and uncertainty associated with wind and solar power generation. Power system stabilizers are commonly used to damp various types of oscillation modes, as from inter-area oscillations in large transmission networks to local oscillation modes of synchronous generating units. This is done by adding a stabilizing signal to the voltage regulator of the existing excitation systems. A PSS power system stabilizer is an additional control system that is applied to an excitation system to provide a better damping response to low-frequency oscillations caused by line faults. The basic function of the PSS is to apply a signal to the excitation system, producing electrical torques to the rotor in phase with speed differences that damp out power oscillations. Below is presented the block diagram of an excitation system with PSS. By introducing the PSS in the excitation system is expected to produce an electric torque component to counteract the mechanical dynamics. Controlling these oscillations can be relatively straightforward by applying a power system stabilizer PSS. Various methods for analyzing this issue have been proposed by researchers. In 1969, DeMello and Concordia explored the stability of synchronous machines under small perturbations by examining a single-machine infinite bus SMIB system through external reactance. Their analysis provided insights into the effects of thyristor-type excitation systems and established the stabilizing requirements for such systems. These requirements included the voltage regulator gain parameters and the transfer function characteristics for a machine speed-derived signal, along with the voltage regulator reference to provide damping of machine oscillations. The study examined a range of machine loadings, inertias, and system external impedances to determine the oscillation and damping characteristics of voltage or speed following a small disturbance in mechanical torque. The researchers aimed to develop unifying concepts that explain the stability phenomena of concern and to predict desirable phase and magnitude characteristics of stabilizing functions. In 1989, Dr. Kunder provided analytical work and a systematic method to determine PSS parameters for large-scale power generation in practical power systems. The basic PSS design idea was based on the stabilizer proposed earlier, but the phase characteristics were obtained using a multi-machine eigenvalue program instead of a single machine model. This work emphasized enhancing overall system stability, considering the simultaneous damping of inter-area and local modes, and discussing the PSS performance under different system conditions. Small signal stability performance tested the transient stability performance of the PSS and its performance during system islanding. This highlighted the importance of choosing appropriate washout time constants, stabilizer output limits, and other excitation system control parameters. Frequency response method used to compensate for the lag between the excitation input and the electrical torque was fairly robust. Chow and Sanchez-Gasca proposed 4-pole placement techniques for designing power system stabilizers, emphasizing the frequency response characteristics of the controller and suggested a simple procedure to obtain controllers suitable for multiple operating conditions, ensuring desirable frequency response characteristics. In recent years, as interconnected power systems have become increasingly complex, the presence of poorly damped low-frequency inter-area oscillations has strained stability constraints and limited power transfer capacity. Therefore, adequately damping inter-area modes is crucial to secure system operation, ensure reliability, and generally increase power stability. Power system stability is defined as the ability of an electric power system, for a given initial operating condition, to regain a state of operating equilibrium after being subjected to a physical disturbance. Oscillatory stability, a subcategory of small signal stability SSS, is defined as the ability of a power system to maintain synchronous operation under small disturbances. These oscillations typically occur at frequencies between 0.2 to 3 Hz with insufficient damping. There are 3 types of oscillations observed in power systems. Inter-unit oscillations typically involve 2 or more synchronous machines at a power plant or nearby power plants swinging against each other, with frequencies ranging between 1.5 Hz to 3 Hz. Local mode oscillations generally involve 1 or more synchronous machines at a power station swinging together against a comparatively large power system or load center, with oscillation frequencies ranging from 0.7 Hz to 2 Hz. Inter-area oscillations involve combinations of many machines on one part of the power system swinging against machines on another part, with frequencies normally less than 0.5 Hz. A power system stabilizer PSS is a control system installed on a generation unit that monitors variables such as current, voltage, and shaft speed. When necessary, it then sends the appropriate control signals to the voltage regulator to damp system oscillations so that frequency does not stray beyond tolerances. Rapid small positive and negative changes in frequency in the range of 0.2 to 3 Hz, called frequency oscillations, occur in bulk electric systems due to small variations in load. These oscillations must be damped reduced to avoid the potential for growing oscillations that could ultimately push frequencies outside of system tolerances. If this happens, the system will begin shutting down to protect equipment, thus resulting in wide-scale outages. When small oscillations occur, the generator's rotational speed increases or decreases due to the frequency fluctuation. However, the turbine control that manages the speed by injecting slightly more or less fuel is not always fast enough to respond to such oscillations. And given that a variety of generators are interconnected in a bulk electric system, each may respond differently, potentially resulting in generators no longer spinning in sync. Thus, it is important to respond to these oscillations quickly. A PSS does this by sending a control signal to the generator voltage regulator when such oscillations are observed. This rapidly changes the generator operation to counteract the frequency oscillations. Stability is an important part of ensuring operability of power generation systems. Large transients can cause power systems to become unstable and can eventually lead to blackouts. Power systems need to be designed to withstand large disturbances and maintain stability under changing operating conditions. Devices such as the Generator Automatic Voltage Regulator AVR and Power System Stabilizer PSS are widely used to manage these system instabilities. These control devices can be attached to power generation systems to help improve stability. The PSS works together with the AVR to maintain transient stability within a power system. The generator's output is primarily controlled by the AVR, but this system alone is not fast enough to respond to sudden glitches or faults. A PSS is added to the feedback to dampen rotor angle swings within a broad range of frequencies. Functions of a PSS. PSS adds a signal to the excitation system proportional to speed deviation. This adds positive damping. Other inputs, like power, voltage or acceleration, can be used. Signal is generated locally from the shaft. Both local mode and inter-area mode can be damped. When oscillation is observed on a system or a planning study reveals poorly damped oscillations, use of participation factors helps in identifying the machines where PSS has to be located. Tuning of PSS regularly is important. Modal analysis technique forms the basis for multi-machine systems. How power system stabilizer PSS works: it is achieved by modulating the generator excitation so as to develop components of electrical torque in phase with rotor speed deviation. The PSS thus contributes to the enhancement of small signal stability of power systems. Benefits: improved damping of the system, the dynamic stability of the system is improved, reduced power losses. In summary, power system stabilizers are important devices that help maintain the stability of power systems. While turning off a PSS can have significant impacts on the stability of a power system, there may be situations where it is necessary to do so. PSS performance is often evaluated based on its local mode damping. A properly tuned and well-performing PSS should provide sufficient damping to local mode oscillations. Frequency analysis can be used to determine the optimum PSS settings based on system characteristics. The PSS should be tuned to provide torque changes in phase with speed changes. Dynamic signal analyzers are commonly used to test the performance of AVR and PSS controls. The frequency response of the system under load can be used to tune the PSS. After tuning the PSS, the frequency response of the PSS can be measured and compared with expected models before being added to the power system. Power system stabilizer structure. The basic objective of power system stabilizer is to modulate the generator's excitation in order to produce an electrical torque at the generator proportional to the rotor speed. In order to achieve that, the PSS uses a simple lead lag compensator circuit to adjust the input signal and correct the phase lag between the exciter input and the electrical torque. The PSS can use various inputs, such as the speed deviation of the generator shaft, the change in electrical power or accelerating power, or even the terminal bus frequency. However, in many instances the preferred signal input to the PSS is the speed deviation. Figure illustrates the block diagram of a typical PSS. The PSS structure generally consists of a washout, lead lag networks, a gain, and a limiter stages. Each stage performs a specific function. Testing of the AVR PSS controls. Testing of the PSS is normally performed during plant commissioning. The test condition for PSS is at or near base load output of the plant. The testing of modern excitation systems is facilitated by the use of internal data recording and test signals. The basic types of tests usually performed are given in the following list. Step test in AVR reference base load without PSS. Gain margin test to determine the PSS gain to be used. Step test in AVR reference base load with PSS. Optional additional testing for new design units or per customer requirements are AVR uncompensated transfer function. PSS transfer function. The tuning of a PSS involves adjusting the PSS's parameters to achieve the desired damping of the system. Proper tuning ensures that the PSS is effective in providing stabilizing signals and improves the power system's overall stability. The tuning of a power system stabilizer PSS is a process of adjusting the parameters of the PSS to ensure that it provides the desired level of damping to the power system. The damping provided by the PSS is critical to maintaining the stability of the power system, particularly during disturbances such as faults or sudden changes in load. The tuning process involves adjusting the PSS parameters based on the system's response to disturbances. The goal is to achieve the desired level of damping without causing excessive oscillations or instability in the power system. The tuning process typically involves a combination of simulation studies and field testing to ensure that the PSS is properly calibrated. The specific tuning parameters for a PSS will depend on the characteristics of the power system, including the generator and excitation system. In general, the tuning process involves adjusting the gain, time constants, and lead lag parameters of the PSS to achieve the desired level of damping. It is important to note that the tuning of a PSS is a complex process that requires specialized knowledge and expertise. Improperly tuned PSS can lead to instability and even blackouts in the power system. Therefore, it is critical to work with experienced professionals to ensure that the PSS is properly tuned and calibrated. How can we tune a power system stabilizer PSS? The function of a power system stabilizer PSS is to extend the small signal rotor angle stability limits of the power system by modulating the synchronous machine's excitation to damp the rotor speed oscillations. To provide positive damping, the stabilizer must produce a component of electrical torque in the rotor in phase with the speed deviations. Different studies shows example in which a rotor speed-based PSS is tuned using a single machine infinite bus system with the objective to achieve a minimum damping ratio of 15% for the system with PSS. Those studies cases corresponds to one step of the following tuning procedure. Step 1, base case without PSS. Case is used to analyze the stability of the system without PSS. A modal analysis is run to identify the dominant oscillation mode of the system, which has a frequency of 1.23 Hz and a damping ratio of 3.35%. An RMS simulation CalmSim is run to verify the time domain response of the system to a step change in the reference signal of the automatic voltage regulator AVR. Step 2, phase compensation requirements. The PSS phase compensation requirements are obtained from the Bode plot of the generator exciter power system GEP open loop transfer function calculated with the machine's inertia set to an infinite value. The Bode plot is obtained from the execution of the calculation of frequency response command ComFreCresp in which the input signal is the PSS input signal UPSs of the AVR, and the output signal is the synchronous machine's electrical torque SME. From the GEP transfer function, the PSS should ideally compensate 88.72 degrees at 1.23 Hz. Step 3, phase shaping. The PSS model is added to the synchronous machine's frame. The time constants of the PSS phase compensation blocks are chosen to match the ideal phase compensation requirement calculated in the previous step. The ComFreCresp command is run to obtain the Bode plots of the PSS transfer function GPSS and the compensated transfer function GEPX-GPSS. The numerator and denominator time constants of the lead lag blocks of GPSS are set to 0.256s and 0.044s, respectively, i.e. each block adding 45 degrees at 1.5 Hz. It is verified that the phase of GEPX-GPSS is 2.8 degrees at 1.23 Hz and lies within +30 degree in the typical range of electromechanical frequencies from 0.2 Hz to 2.0 Hz. Step 4, PSS gain selection. The modal analysis is iteratively run for increasing values of PSS gain K until the damping ratio of the dominant mode is at least 15%, the selected value being 24 pu. The time domain response of the system to a step change in the AVR reference signal is simulated and compared with the response without PSS step 1 in the same plots. The following scripts provided in the scripts folder of the project library can be used to aid in the tuning process. DPL command lead _lag _time constants calculates the time constants of two first-order lead lag blocks for given center frequencies and maximum angles. Python command wrap to 180 wraps the results of the phase Bode plot to plus or minus 180 degrees. It must be executed while the plot page with the Bode plot results is being displayed. A similar procedure can be applied to tune power damper controllers pod installed in inverter-based resources, fax devices, or HVDC converters. In those cases, the proper pod input and output signals must be selected and the ComFreCresp configured accordingly. Here are the steps involved in tuning a PSS. Identify the oscillation mode. Identify the dominant oscillation mode in the system that needs stabilizing. One of the commonly used methods for identifying the oscillation mode is the modal analysis. Select PSS type. Select the appropriate type of PSS to be used based on the generator and system characteristics. The most common types of PSS are lead lag and washout PSS. Select tuning parameters. Determine the tuning parameters, which include gain, time constant, and washout coefficient. These parameters need to be optimized to provide the desired level of damping for the identified oscillation mode. There are various tools available for PSS tuning, such as MATLAB, PSCAD, or PTI software. Conduct a simulation. Run a simulation to verify the performance of the PSS. The simulation should include the PSS, generator, excitation system, and the power system. Various operating conditions should also be simulated to ensure that the PSS provides stable performance in different system conditions. Field testing. After simulation testing, the PSS should be tested in the field to confirm its effectiveness.
Field testing should be done under various system operating conditions to ensure the PSS's stability and effectiveness. Fine-tuning: fine-tune the PSS if necessary, based on the results of field testing, to ensure its effectiveness. Tuning of PSSs is a complex task and requires expertise and experience in power system analysis and control. Proper tuning of PSSs is critical to ensuring that power systems operate reliably and avoid instability and blackouts. There are smart techniques for tuning power system stabilizers PSS, including trial and error method. This involves adjusting the PSS parameters based on the response of the power system to different disturbances. The parameters are adjusted until the desired level of damping is achieved. Frequency response method. This involves analyzing the frequency response of the power system and adjusting the PSS parameters to provide the required damping at the critical frequencies. Model-based tuning. This involves using mathematical models of the power system to determine the optimal PSS parameters for the desired level of damping. Optimization-based tuning. This involves using optimization techniques to find the optimal PSS parameters that minimize a certain objective function, such as the time domain performance or the frequency response. The choice of tuning technique depends on the complexity of the power system, the available data, and the desired level of accuracy. It is important to note that the tuning of a PSS is a complex process that requires specialized knowledge and expertise. Therefore, it is critical to work with experienced professionals to ensure that the PSS is properly tuned and calibrated.